Okay, well, it looks like it's the top of the hour, so we will go ahead and get started on this webinar today. As you can see on the screen, this is going to be presenting SIMSOLID for large assembly analysis in Fusion 360. My name is Aaron Magnan, and along with me I have Ken Welch from SIMSOLID. Very happy to have him on board to help show and highlight the power behind this tool. It's pretty darn amazing, to be honest. So real quick about me, I am a mechanical engineer. I have some experience in FEA, CFD, and injection molding software. I'm on Twitter, so connect with me if you have questions. If you do have questions during the webinar, please use the GoToWebinar interface that you'll see on the right-hand side of your screen. Just hit the little red arrow to expand it out and to type those questions in. We do have with us Ken Welch. I'll let Ken go ahead and introduce himself. Ken, you there?
Yeah, I'm here. Well, let's see. There's my background. I'm just a guy that's been around the analysis world for many years. I was at a number of companies, PD Engineering, Patran, and Rasna with Mechanica and Moldflow, MSC Software. I was prior to founding SIMSOLID. I was the VP of Strategy for MSC. So
nice little resume.
Anyway, probably enough about me. Should we get going on the presentation?
Yeah. So why don't you tell us a little bit about SIMSOLID?
Okay. Well, cool. Well, listen. So SimSolid. It's a new analysis product, and really remember just a couple things about it. One, it solves the original CAD geometry with no simplification. So you leave in all the detail and you just solve it as is, and it doesn't create a mesh. There isn't a meshing process. The other thing to know about SimSolid is it solves two types of models that are very interesting. One are big assemblies. So if you have large assemblies that you don't really want to tackle with traditional FEA, that's a target for SimSolid. The other thing is really complex geometry. So a lot of these lattice-based design type things, they're very complicated, and that's another kind of sweet spot for SimSolid. So because of that, SimSolid is like a perfect complement to Fusion's embedded Nastran. It extends it for big assemblies and these complex parts, and that's where I think it really fits.
Yeah, and so although we've highlighted this as a simulation solver for large assemblies, it does all kinds of things. And I don't know about the viewers out there, but I was a little hesitant when I heard no mesh. But with what I've been able to see so far and what I've been able to run, the complexity of the geometry, it's absolutely incredible. So we'll just switch tabs here and let you continue on.
Okay, well, cool. So anyway, it does have a different kind of modeling paradigm. So, in SimSolid, you can have multi-scale kind of geometries, big and small parts or thick and thin parts. You can leave in all the features like you see down in the lower left side. There's a bunch of very small holes and detail that you typically never leave in a traditional model. No problem with SimSolid. In fact, if you have very complex surface patches, that's okay. Even that you see the picture of the man there, but extreme geometric complexity, and we've done some very complex STL type mesh bodies. We can handle that as well. Probably the most interesting thing though about SimSolid is our ability to handle connections between parts. We have a very elegant way to do connections so things with parts that have a little bit of overlap or some separation or kind of what I would call a ragged contact surface. That is really our sweet spot. We can really handle those things great, and I hope to show you that this morning with the demo. Maybe the next slide. So the technology in itself, that's a presentation, a separate presentation. But what I will say about it is that what we're using is extensions to the method of external approximations. It's an adaptive solver, so it's like kind of adaptive H or adaptive P solvers in the traditional FEA world, where we take an initial set of equations and then we locally enrich it on a pass-by-pass basis, looking at the errors that are in the model and to minimize the errors. So it's that kind of process. There's a lot of information though on the technology on the SIMSOLID website. So if you go to simsolid.com white papers. We actually have much more than white papers there. We actually have a validation manual, we have a quick start guide, and we even have an unpublished book on the theory of external approximations that my co-founder Victor Panovich wrote. It's a very detailed book. It's about 300 some odd pages. So if you really want to get into the background, there's a lot of information on our website.
Yeah, I'll crack that open tonight, I think.
Okay, there'll be a test tomorrow. Okay. Maybe before we start, I just want to give one customer example. I think it's always good to put into context. This is a company, Serapid, and they have an interesting vertical chain lift technology. You see it there on the left. It actually lifts these platforms up and down. These are often used as theater stages, so it's the stages that come up and down. And their challenge was, these are very complicated assemblies. You can see that just the chain by itself is 324 parts, and including the scissor lifts and things like that, their models were pushing 1,000 parts. They found that using SIMSOLID, they could analyze this entire assembly on a design basis. And what I mean by on a design basis is it wasn't just to validate; it was to help size the design. So they would use it iteratively as they were using their design software, and then going into SIMSOLID to evaluate the performance.
Yeah, you can spend quite a lot of time taking a model as designed and do all kinds of simplification before you actually go into an FEA. So that's pretty amazing. They can just use the model directly as is. Definitely not the norm when talking about FEA. Well, thanks for that, Ken. I'm going to take back over for a little bit here, just to show everyone a little bit about Fusion 360. I don't want to go too deep into this. I assume that everyone here already has some sort of background on Fusion 360, so today's really about SIMSOLID. Real quick though, before we pass it back over to Ken, Fusion 360 is your full design and product innovation platform. It has CAD, it has CAM, it has some simulation already built in, and it works on both Mac and PC. So I know that I think like 25% of you out there are probably using Macs. I use a Mac. Right now I'm actually in a cloud computer that is on a Windows build. It is the complete design environment. I mean, you can start from your industrial design work using your T-splines, push and pull technology. I absolutely love that. It's so much fun to work with. You can really create some powerful stuff using that, and then take that into a mechanical, more of a mechanical design to actually make producible parts, make those drawings, create those renderings for marketing purposes, and run those simulations and create those CAM toolpaths. So it really does everything that you can imagine when you think about developing a product. But it also, due to its cloud-based nature, it has this added ability to open up collaboration and team efforts across the globe. I mean, it really doesn't matter. All you need to do is be connected to the internet somewhere, somehow. So I do have a little video that I put together here that is going to highlight how to get and start using SIMSOLID. I'm not the expert here. Ken is definitely the expert when it comes to SIMSOLID, so I'm not going to spend too much time on this, but I just want to show you how to go and get it. So essentially, to get and install SIMSOLID, you're going to jump into the add-ins, and sorry about the quality here. It should increase a little bit. It's on YouTube. But you go to the add-ins, jump to the CAE side of things. You'll see SIMSOLID there. SIMSOLID is on Windows. It is on 64-bit Windows. You hit the download button, and in absolutely no time, you're going to be installing it. Installation for this is literally like 2 minutes or something like that. When you click Finish and jump back into Fusion 360, all you're going to see is this button here. And this button is really where you get a lot of the SIMSOLID power. Using the drop-down, you'll see the ability to open your model into SIMSOLID. You can export a file to SIMSOLID, and you can also jump into some settings here. The resolution here I changed to fine. Ken does not recommend you do that. I mean, there's very few cases where you actually need to use the fine, because there are those internal algorithms to ensure the quality is upheld.
Yeah, they just the fine. Typically you don't need to change that unless you have some really weird doubly curved geometry. Typically, you just leave it at standard.
Yep. So definitely. Let's just start with the standard is what we typically recommend, even when using simulation in Fusion, the built-in stuff. So it's a good place to start from, and then you can expand from there. And as Ken mentioned, there's a few cases where you actually need to use Find, but it's up to you to figure out when that might be. Once you get into SimSolid, there is a 30-day free trial. Here I'm going to show the setup. Basically, just type in your email address, type in a little bit of information about yourself on the next page, and you'll get an email with the activation code. You type it in here, hit activate, and you're pretty much good to go. So for first use in SimSolid, I'm going to jump into this fast start guide in this document. It is recommended to me. Ken recommended it to me as well. It's a good thing to be aware of, and just make sure that you're considering all the important details behind SimSolid and in the approach to these simulations. So it is just a PDF. It is pretty detailed. There's, I think, 70 pages of this, and I'm just scrolling through, just kind of give you an intro to what it is. But once you have your file in SimSolid, it'll do a material import. You saw there that it was actually finding a material that existed in our Fusion 360 document that wasn't in SimSolid. So it gives you the ability to add that automatically. Right now, what it's dealing with are contacts, and I think Ken will probably jump into contacts in more detail as he actually gets into presenting SimSolid in more detail. But the way that SimSolid is able to deal with thousands and thousands of contacts and gaps, like we mentioned, your design model isn't necessarily the best model that you would want for like a simulation's sake, because there are those tolerances and there are those gaps. And what this tool actually does is overcomes those with this algorithm that they're going to use. Once that's dealt with, you jump into the typical setup of an FEA, defining the analysis type, defining the fixtures, defining the loads, and from there you just need to go and solve this. It will solve very, very complex geometry in a very short amount of time. This is a video. I think I did speed it up a little bit, but Ken is going to be running some live for you to see, so it's not something that will take any serious amount of time. Once you have your results, you jump into post-processing. You can start to look at things like your displacements, your stresses, your strains, etc. All those things that you'd expect to see. And again, that's something that Ken will probably be covering in more detail than I'm actually going to be doing here.
Cool. Okay, well, I thought I would do a real quick demo to kind of show you, what this large assembly analysis is all about. So what I did, everybody wants to solve a beam. So I said, well, I'll just do a simple 4-bay truss. It's not as simple as you think, though. Let's just kind of zoom in. It's got full detail. So it's got, hollow tubes. It's got solid bars. It's got, welded structure, and it's got, full fidelity bolts, nuts, and washers. There's a mid side, these mid couplers, and then there's the same kind of detail at the top. So it's pretty complicated. The way it works with SimSolid is so if we want to do, let's assume that we want to do a vibration study of this tall structure, and then we want to do a design change and see how that affects the performance. Well, in SimSolid, if you just pick this, it will just open up the current geometry, the current visible geometry, the either bodies or mesh bodies. So it won't take surfaces. It has to be solid. So any bodies or mesh bodies that are visible, it'll just come into SimSolid. So I pick the button. I say I want to go to a new setting, and SimSolid will pop up, and it brings the geometry in. And as Aaron said, you make these connections. What it's doing now is it's going through a process to search the model and find all the connections between all the parts. And this will take just a second, but maybe, while it does, we can look, this is, about 545 parts. So it's a fair size model. In fact, we bring in, as Aaron said, we bring in the whole assembly structure and any associated material properties. So if you have properties in there from your design, those come in as well. But maybe just to show you, let's pick that, and let's pick the bolts, and then let's hide the unselected parts. just to show you what you get in SimSolid, you get exactly the same detail that you had in Fusion. So, whatever it was in Fusion, it comes in SimSolid. Okay, let's do a quick analysis. So, SimSolid could do static, modal, thermal, or nonlinear static. Let's do a modal. Let's just go and grab let's calculate the first 6 modes. And let's assume this is constrained to the base. So let's just go and pick the base there and say we'll constrain that. Okay. Well, that's all I got to do. I don't need to do any meshing. So I just say pick this button here to say solve. So now what happens is it creates, as I said, this initial equation set. It solves it multiple times. The default solution settings for SimSolid is 3 passes. And each pass, it evaluates the errors and then enriches the solution locally and repeats. So that's pass 1, that's pass 2. We're on pass 3. Aaron, this is where you have to tell a joke. We're almost done.
Where's Alexa when you need her?
You just fill up the time. There you go. So anyway, I like to run stuff live just to show you, we're really, the goal of SimSolid is to be the design tool. Design analysis means you have to be at the pace of design. So this was 31 seconds to solve. And we can go back and look and say, let's look at let's just animate the modes. So here is the first mode, as you'd expect, kind of bending that way. And it's 1.8 hertz, very low frequency. One symmetric mode that way. You get 2 symmetric modes this way. Looks like a torsional mode there, and then a higher frequency mode there. Okay, so so you can extract the modes, and we could have done a structural analysis as well. But let's change gears a little bit here, and let's say I want to understand what the impact on a design change is. So of course, design, we have to go back to Fusion. And in Fusion, any change I make, let's assume that I want to add a horizontal truss. Okay, so let's look at the full model. I want to take one more bay and stick it out the side here. Now you probably notice there's a problem there in that I have 2 bays there. I haven't actually built anything here to support it. So all I really want to do is say, how does this additional piece of mass affect my vibrational characteristics? I don't want to spend the time building this support structure just yet. Well, we can handle that in SimSolid. So let's try a little trick to actually model this assembly directly. So let's go back to SimSolid. Now this time, instead of going to a new model, let's go to that existing model. And as we do that, it'll come in, but does a little bit different. It makes a design study. So you see that in the design study it takes all the changed geometry to the second study, but it copies all the analysis loads and constraints from the first study down. So if you had 4 or 5 load cases and modal, static, thermal, all of those would be copied down and applied as it can. Now you notice that the contact condition is a little bit red. This had a little bit of a, there's a question is, how do I handle this stuff? Well, so that we have to do on our own, but it's pretty easily done. I would come here and I would create what we call a virtual connector. So what a virtual connector does, it basically rigidly connects different pairs of surfaces. So by picking those 2 surfaces, I'm in effect saying I'm going to assume there's like an invisible rigid block between those, and they'll move as one. So simply doing that, and now I can go back and recreate my other connections. Let's just do that really quick. Doing that, I will be good to go to analyze this. So again, I've just done that one thing. It's building the connections back up, but it's already got the analysis definitions ready to go. So give me a second here, and then we'll fire off the second analysis.
I really like how it handles bringing in the second case of that, bringing it as a design study. That's amazing.
Yeah, so it really does save a lot of time, right, to bring it in like that. Now I'm doing the second analysis. So, let's just look at that while we're waiting. This one's much more complex. It's 728 parts. So, this, we brought in a bunch of bolts, these cross members. So, it gets to add up pretty quick. It'll solve a little longer, but not too bad. So let's see, we're already past, past 2, past 3.
And each one of those passes is increasing the quality of the results, correct?
The qualities. It's like you're it's like H adaptive in FEA. You're solving it. You locally think of it as locally remeshed. We don't locally remesh, but we locally enrich the solution, and then solve it again and look at the errors. Yeah. So we're done. So just for comparison, that took us about 37 seconds. Okay, 37 seconds to solve that. This one took us 31 seconds. And so there was our first set of modes, right? If I want to see the second set, I don't need to actually do other than just pick down here. If I pick there's my second set. So I can animate those. There's my 6th mode. I mean, there's my first mode there, and you notice that as you'd expect, more mass up there, it's going to make your frequency is going to go down a bit. Those are 2 modes there. You got a mode like that. And it's interesting, but see how this really nice, that virtual connector really did, these are just rigidly attached there. So, of course, that's an approximation. You have some flexibility in that connector you're ultimately going to build, but it's a pretty good estimate to, say, within a minute or so, I have now calculated the vibrational characteristics of almost nearly 800 part truss. So that's what SIMSOLID is capable of doing. Number 1, large assemblies. Number 2, design iterations. And number 3, it's really well connected with CAD. You can see I just love Fusion. It just you can see how slick it is to go in there, make a design change, and come back to SIMSOLID. So it's a really good solution. Let me just show you one more thing, and I won't solve this. I'll tell you about it though. So the other thing that SIMSOLID is good for is really complex geometry. So this model is this X-Vein drone. It's really a cool model. It's got this generative designed structure. So you can see it's only about 126 parts, but it's got some complexity. So I got this from the Autodesk guys, and I think it's really cool to solve. So what I did was I said, okay, let's just look at it really quick. I assumed that the engine mounts, all things in dark blue, were just rigid. So I said, make those rigid, make the camera assembly rigid, and then we'll just solve the flexibility of this lattice type structure. So I did that, and then I just said, give me the first 6 free modes. And the modes, give me the first 10 modes, 10 flexible modes. The modes took about 4 minutes to calculate, so I won't run that live for you. But you can look at it here, and here is like a mode shape, right? So you can see what it looks like. So 4 minutes we can get something like that. And then I also did one stress, and the way I did the stress analysis, it's not connected; it's supposed to be flying, right? So we have inertial relief. So I turned on inertial relief, and then I just put one set of loads that was 100 newtons vertical that was evenly divided between the 4 engine mounts, so 25 newtons upward on each of the engine mount points, and I said solve. And that took about 3.5 minutes to solve. So, not as quick as that other thing. It's very complex geometry here, many surfaces. But what I did was I came straight from CAD, took the materials off of the CAD system, brought it in, did both modal and structural analysis in under 10 minutes with SIMSOLID. So I think, for if you have really complicated parts or really big assemblies, that's really the sweet spot of what I think SIMSOLID could add value to you. Okay, that's my demo, short and sweet.
I can take it back. I was just going to say that's a great example for inertial relief. The geometry in this case on those wings, is that STL meshes or is that solid?
No, well, we can do either one. So if you look at, we can do mesh bodies, which are just like STL, or we can do surfaces. I think what this was, actually I know what it was, they actually took that and they built surfaces. These are actually all fusion surfaces. It's pretty impressive when you look down here. Yeah, but we could do either way. If it was a combination of mesh bodies and bodies, we can solve that as well. So in Fusion, you can have these mesh bodies, what I think is kind of cool. At the same time, you can have it in a assembly with a body. We can handle both of those, and we can do the assembly between the mesh body and the body and analyze it directly.
Yeah, it's pretty incredible. I mean, I don't know of any tools that will actually solve for like an STL mesh. So that opens up some new opportunities for some models that I have.
If you go to the Fusion's got a great gallery, and if you go to the gallery, and Aaron can tell you how to get there, and just search for SIMSOLID, I think we actually just put up the X-Vein model today, so it's there as well. But you can see a whole bunch of examples of Fusion working with SIMSOLID, and a number of them have videos, and a number of them actually have geometry you can download and try. So it's a great place to kind of feel your way as to what's possible with these two great tools.
Yeah, I'll show how to get there when I jump back into Fusion in just a moment here, but we'll switch slides for the last one here.
Yeah, so I guess, just to say, so SIMSOLID is, it's the way we license it, it's very easy. You can get it, it's a subscription, either a monthly or an annual basis. It comes, the plugin is free. You can just get it from the App Store, like Aaron showed, and it comes with a 30-day trial of SIMSOLID. Today it's Windows only, so your Mac guys, we're only Windows today, Windows 64. There's nothing to say that we couldn't be Mac in the future. We'll just need to work with the Autodesk guys, and we can get there. But today it's Windows only. What I would say about if you look at what people tell me, and maybe just to close, is that they said, Ken, this is really a life-changing product. I mean, it really changes how I think about analysis, and especially, if you just think about the model I just did, just to build the mesh on that model to solve it like that X-Vein, would have been, half of the month of our monthly subscription. So people tell me that just in terms of productivity, there's really nothing like it. And we're very excited at SIMSOLID to bring it to you. We think it's an outstanding tool that has a really kind of a unique niche in the market. It's not really where you think of this traditional FEA, so it kind of extends the traditional FEA out, and I think it works great with the other tools.
Well, thanks everybody for attending. Wish you guys all a great week and great 2017 as well. Have a good one. Cheers.
Okay, thanks guys.